Okay, so in my previous lecture on simulation, I had stopped at this point where I had shown you how you can recover or check whether your model can recover parameters in a fairly straightforward linear model. And so now what we're going to talk about, slide 49, is the situation where we have not one data point from each subject in each condition, in each of the two conditions, but multiple data points. So in the previous data set that we had generated, the simulated data, we had exactly one data point from each subject in each condition. So that's what this output is showing you, right? But in real life, when we are actually collecting data, what we typically do is that we have more than one data point for each condition from each subject. So for example, we might generate, or we might have 20 data points for each subject in subject relatives and 20 data points from each subject in object relatives. These multiple data points from each subject in each condition is going to be called a replicate. Okay. So the way we generate these replicates is the following. We're going to define the number of subjects, n is equal to 10, and then the number of replicates, k. In this case, I've taken 20. You could take whatever number is reasonable for you in your context. And here again, what I'm doing is I'm setting up the conditions vector as a sum-coded vector. And this time, I'm going to have each one of these levels be not n times in length, but n times k. Because each subject, each of the n subjects is going to deliver k data points. Therefore, it's going to have to be, each of these contrast codings will have to be n times k repetitions, right? Okay, and so the subject vector is going to look like this. It's going to go from 1 to n, but each of those numbers is going to have to be repeated k times, right? Because each subject is delivering k data points. So basically we are repeating each number id for each subject. And so once we've defined the condition vector and the subject vector, we can assemble the data frame, which looks like this now. So I have multiple instances of subject 1 with the same condition. That's because I have multiple replicates from that subject, right? Okay. So now once I have these multiple replicates from each subject, I can now generate repeated measures data in the following way. Okay, so what I'm going to do is I have my fixed effect intercept, right? So the grand mean intercept is 725, and I'm going to add to that, what am I going to add to that? The fixed effect of condition, right? So there was a 50 millisecond effect with the plus minus 1 coding. That means that we're going to have a 25 millisecond slope, right? And finally, this is the simple linear model. And then we have the residual noise factor there, which is going to be which is going to have a mean of 0 and a standard deviation of 300. And what will be the length of this vector? So there are two conditions, subject and object relatives, and each of them is going to have n times k data points. So that's why I have n times k times 2 residual, the vector is of that length, right? All that I have not explained yet is this line here. Okay, so what I'm doing here is, first of all, I'm generating for each of the n subjects, I'm generating a random intercept. Okay, and then what I'm doing is, after having rounded these adjustments by subjects to the intercepts, I'm replicating each one of these k times. Okay, so if I have subject 1, I'm going to have generated that subject's varying intercept adjustment. I'm going to have to repeat that k times. Why? Because I'm going to have k instances of subject 1. So I'm going to have to put the adjustment k times there. So that's why I've got a repetition here, and then I'm going to have to do that twice because I've done it once for subject relatives, or whichever coding this was, I've forgotten. And then I have to do it for the other condition as well. That's why I've got two rep commands here, because I first repeat the subject adjustment to take into account the replicates that I have from the subject, and then I do another repetition of the entire vector of subject adjustments with the replicates for the other condition as well. Okay. All right. So this on the surface, this piece of code here, this looks very challenging, but let me unpack it, so that it doesn't the complications become quite easy to see. So I'm going to now explain how this I'm going to explain again how this vector comes about. Okay, just to be very clear about how this works. Okay, so let's break it up. Okay, first let's break it up into the smaller part where I've got the subject adjustments generated once. So I've got n subjects, so there's going to be n data points, and each of these numbers is going to reflect the subject adjustment to the intercept. Okay, this is the varying intercept here. So this is the vector u0, right? And so then what I'm going to do is I'm going to repeat each of the values in the u0 k times, right? So you see that 11 is repeated 20 times, minus 220 is repeated 20 times, and so on, right? So then what I'm going to do is that I'm going to now have how many 10 subjects and 20 replicates. So I'm going to have 200 data points for subject relatives, and then I'm going to have another 200 data points for object relatives. So I'm going to have to repeat that vector for the object relatives again, and that is going to give me 400 data points in total. And just as a sanity check, you can check that the dimensions of your data frame is actually 400 by 3. So that vector of data points, the subject adjustments, will span the entire length of that data frame, right? Okay, and you can also check, if you want to, that each subject is delivering 20 data points in each condition, right? So what I'm going to do is, what I've done here, is that I've basically added a subject adjustment. This is what I showed you here, right? This is a very long command here, which I unpacked for you just now, which shows how I created a subject adjustment in this data frame, in the vector for generating the reading times, okay, the simulated reading times. Okay, so now once we have the data in this form, what we can do is we can fit a linear mixed model with varying intercepts, for example, right? So we can start with a simple varying intercepts model. I've switched off all the warnings, as you can see, because I want to just focus on the simulation right now. Okay, so we can also fit a more complex varying intercepts and slopes model. That's what I've done. That's what I've done here, right? And when I do that, when I fit the varying intercepts and slopes model, I should get an output that's something like what you see on slide 59. Of course, your output will be different if you run this code yourself, right? It will look different. And so what you see in this code is, as usual, there is the fixed effects estimates with their standard errors and t-values, and there are the three variance components. Here's the intercept adjustment standard deviation, the slope adjustment standard deviation, and the residual standard deviation. Notice that the correlation between the intercepts and slopes is +1. So that means that there's a problem in estimating that parameter here, because that's an extreme value. And if you remember the linear mixed modeling lecture, this is an indication, a +1 or -1 correlation is an indication that the Elmer function is failing to estimate that correlation parameter. All right, so now what we can do is, until now I had only been adjusting the intercept, right, by subjects, right? So now what I'm going to do is I'm going to adjust the slope as well. That means I'm going to assume that some subjects have larger relative clause effects and some have smaller effects. Okay, so we have seen that kind of model before. So I'm going to assume that subjects have the standard deviation of the varying slopes is going to be 50 milliseconds. Okay, so I've just chosen 50 arbitrarily just for illustration purposes. There's nothing deep there, right? So I'm going to create a vector u1 which now represents my slope adjustments. So this slope adjustment, these are 10 subjects, 1 2 3 4 5 6 7 8 9 10, right? So the first subject that I've randomly generated the slope for has a slope that is larger than the average slope. This third subject has a slope that is smaller than the average slope, and so on, right? So these numbers will vary each time I simulate data, because I'm simulating getting new subjects, and every subject is going to be different, right? That's the reason that these numbers will differ. Okay, so now I've got the slope adjustment. So the way that the slope adjustment will go into simulating data is that when I have the slope term, which is 25, if you remember in our model, when we generate simulated data, we've got the slope at 25 and we multiply it with +1 or -1, right? So that's the average slope, ignoring the individual variation. So now what we are adding in this line here is that what we are adding is the slope adjustment to the fixed effect slope, and I'm putting it in brackets because I'm going to multiply both these terms with +1, which is one of the relative clause levels, right? So what I'm doing here is, for object relatives which are coded as +1, I can now generate, having generated random adjustments to the slope, I can take the fixed effect value 25 and the random adjustments to the slope for the 10 subjects and generate the varying slopes for the subjects in this particular instance, right? So I've got the first subject has a very large slope. That means the object relative has a positive. That means object relative is slower than a subject relative, and here I've got a negative slope, right? So it's the opposite pattern. That means that different subjects are going to have different effects now, right? And so, am I saying this correctly? This is so actually I should be looking at the differences. What am I doing here? Yeah, sure, right. Sorry, I was correct here. So what's happening here is that this is a positive adjustment to the average effect. So it's larger than average, and this one is smaller than average, right? And so on. The negative ones are smaller than average, right? Okay, so basically now we can also plot this by subject variability, right? In the mean subject relative between the subject and object relative effects, so every subject is going to have a different effect for subject and object relatives, right? So what this is only for illustration. We are never going to publish such a plot, or we are never going to display it in a paper or anything like that. This is only for you to notice that, for example, the subject relative clause value for this subject is this one here, and the object relative clause value is here, right? So the different subjects have different effects for the subject and object relatives. That's the variability that is induced over this fixed effect. So if we did not have any varying slopes, then all subjects would be assumed to have the same slope of 25 milliseconds. So this varying slopes is adding variability in this estimate. Okay, so now that we can generate different slopes for different subjects, we can now incorporate that into the simulation, right? And just into simulating data. So the way I'm going to now simulate data is that I'm just going to add one more thing into my simulation line, right? So I had earlier, what I had was the fixed effect 725, the subject adjustment, right? I explained this extensively just now, right, to the intercept. And earlier I had only 25 here. This was just the number 25, multiplied with +1 or -1, right? And then the residual standard deviation, the residual error, right? So the only innovation now is that I have, instead of writing 25 here, I'm going to write, oh gosh, here. Instead of writing 25 here, I'm going to adjust 25 by subject. And I'm going to do it exactly the same way as I adjusted the intercept, except that I have a different standard deviation of 50, right? Remember, I set up the varying slopes to have a smaller standard deviation. So what I'm going to do now is I'm going to generate data for n subjects from this normal distribution, and then I'm going to repeat each one of those numbers k times, and then I'm going to repeat the entire vector twice, one more time, right? So that I have the vector for subject and object relatives. And that's it. Now I can generate data that actually has varying intercepts and slopes, right? So one thing I want to show you here that is very important is to learn how to visualize the by-subject effects, right? So one way to visualize them is by using a function like this ggxy plot that I've written here. You can download it and look at it later, and you will encounter it again in the homework assignments, okay? What this function is showing you is that for the 10 subjects, I'm displaying these subjects, in this case simulated data, but I'm displaying the subject, each participant's subject and object relative clause data, and I just fit a linear model on each subject's data. And what this what purpose this serves is that it allows us to visually check how much variability there is in the subject object relative clause effect between subjects, right? What we are seeing here is that some subjects have a slope going down this way and some subjects have a slope going this way. So there's quite a bit of variation in the slope here, right? That's what that 50 millisecond effect is inducing, right? So every subject has a different slope. The x-axis is slightly misleading here. I'm sorry, I should have fixed this. It should have been just -1 and +1. These numbers are not relevant here, right? Because this is just a +1 -1 coding. There's nothing in between. And on the y-axis is reading time, and so you can see that there is some variability here, right? So we can now fit a model to the simulated data, right? And we can fit a model with varying intercepts and slopes. Notice that I'm not assuming any correlation here, because earlier I already realized that that was not a good idea because I was getting a +1 correlation. So I just dropped it, right? So now I don't have any correlation parameter here, as you can see, and everything else is pretty similar. Of course, I have different numbers here. And the reason for that is that I have generated new data. Every time I generate data, I'll get different numbers. When you rerun this code yourself, you will find that you will get different numbers than me, obviously, right? You're generating your own data now. Okay, so this model that we have just written up can be written like this. We can say that our reading time is generated from a normal distribution with some intercept, fixed effect intercept, some intercept adjustment by subjects, and some fixed effect slope beta 1 with some adjustment u1, right, to the slope. This whole term has to be multiplied with the condition coding to get the +1 -1 coding to ensure that you get the correct simulated data for each condition. And this is the residual standard deviation, right? This is one way to write the model, okay? And these are the two variance components in addition to the residual standard deviation, okay? So these are 3 standard deviations that we will be estimating in the model, and you saw that here, right? We've estimated 3 standard deviations: the intercept adjustment to by subjects, the slope adjustment by subjects, and the residual error. Okay, so now where was I? Right, so I just said that there are 3 variance components, and these I just explained to you, right? So I'm not going to repeat this. I'm just pointing out what the 3 variance components are, okay? All right, so now I want to show you a more sophisticated approach for generating generating the data, generating the random effects, basically, right? So the way that we have been doing it right now is that we've been using this rep command repeatedly, if you remember. It's kind of it's okay, there's nothing wrong with it, but it's a bit ugly, right? This rep command is could be improved on a little bit. Okay, so I'm going to show you a little bit a slightly better method for generating the random slopes and also intercepts, actually. Okay, so let's see, where are we? Right, so this is where we're at. So what we're going to do now is that let's say we have 10 subjects and 20 replicates, right? And so we're going to do the usual thing that I've already shown you. This is not new. I'm going to generate my condition vector and generate my data frame with the subject set up correctly and the condition vector set up correctly. Okay, so now I'm going to add to this data frame. I'm going to add the simulated data in the following way. Okay, so first I'm going to generate a data frame. I'm going to generate a matrix called which I will call the U matrix. Okay, small u, small case u. I'm going to generate a U matrix that's going to contain the intercept adjustments in the first column and the slope adjustments in the second column. So what I'm going to do is, if I have 10 subjects, I'm going to have 10 rows in this U matrix. The first column will have the intercept adjustments, the second column will have the slope adjustments. Okay, so that's what I've done here. What I've done is I have set up the standard deviations for the intercept and slope adjustments, 250, right? And then I created a subject vector going from 1 to 10 in this case, and I created a column called U0 that has the intercept adjustments, which I've just generated here, and another column called U1 which contains the slope adjustments. Okay, so this U matrix is now going to contain the intercept and slope adjustments. Now, the reason I've created this U matrix now is that I can look it up. I can look up the U matrix. When I want to know subject 1's intercept and slope adjustment, I just look up this U matrix, look at the first row which contains the first subject's data, and use the intercept and slope adjustment in my data generation function, for generating simulated data. So how do I do this? Let's do this. Take a look at this. This is what my U matrix is going to look like. The first column tells me which subject I'm talking about, and the two columns tell me the intercept and slope adjustments for that particular subject. Okay, so what we're going to do is that for each row in the simulated data frame, the SimDat data frame, we're going to look up the subject ID in each row, and when we're going to find out from the U matrix what the intercept adjustment is, and we're going to find out from the U matrix what the slope adjustment is for that subject, right? And then we're going to plug in that value, the U0 and U1 value for that subject, into our data generation function for the particular row in the data frame. So what that means is we're going to go row by row. Where am I? Sorry, where is it? SimDat is here. I'm going to go to the first row, look up subject 1. Subject 1's intercept and slope adjustment can be found in the U matrix, right? In this U matrix, here it is, right? 83 and 26, and I'm going to use that to plug into this command and write a random value, the random simulated value for that subject in that row of the data frame. That's basically it, right? The rest is now technical details. I'm going to show you how this works, right? So let me make this a little bit bigger. So we begin here. What I've done is I've set up the number of rows in my simulated data frame, right? And then what I've done is I've created an RT vector which has as many empty cells as there are rows. So I'm going to fill in this RT vector row by row. Okay, and so then what I do is I set up my fixed effect intercept and my slope here, and my residual standard deviation. These are my fixed values that I will use for generating the simulated data. Then I'm going to go row by row as follows. Okay, in every so for every row I'm going to take the beta 0 value, which is 725, and add to it the value in the U matrix so that's the column in the U matrix that corresponds to the ith row in the simdat data frame, right? So this command here, simdat I with a comma after that, is isolating the ith row of the simdat data frame, and then this command here, the $subj command, is looking up the subject ID. So this entire command is going to serve the purpose of giving me a number, which is the row of the U matrix, right? So if this number is, for example, 1, what that tells me is that I'm looking for the first row of the U matrix, and I'm looking at the U0 value in the first row of the U matrix. What's the U0 value in the first row of the U matrix? That's this number 83, right? So that tells me the intercept adjustment for this subject here. Now it just happens that the first row, where is it? The first row of the U matrix happens to be the first subject's data. That's how I set it up. Okay. All right. So the same thing happens here. I look up the subject ID for the ith row of the simdat data frame, and I'll get a number here which tells me which row in the U matrix to look at, and then I just look up the U1 value, which is this one here for the first row, right? 26. So that's the number that I'm going to plug in, right, dynamically as I go through this for loop. I'm going to keep adding intercept and slope adjustments by subjects. So this is a very general way to add intercept and slope adjustments into your simulated data, right? So when you're generating data with intercepts and slope adjustments, right? So the big development here, I've already explained it, so I'm not going to belabor this point now. I'm just spelling out in these slides here exactly how I produced those simulated data here. Okay, so you can look at these slides yourself and ask me if you have any questions. I think I explained this just now, right? All right, so so this is all straightforward now since I've explained this. Okay, so basically that's the situation. That's the place where we are at now, right? What we have is that you can now generate data that has varying intercepts and varying slopes, right? And of course you can also check whether your parameters can be recovered by the model. That's something you can do yourself to see if it works. Okay, so so I think that we are now at a point where we can play a little bit with the stuff that we have learned in this lecture, and so I will stop here and continue this lecture in the next part of this video, in the fourth part of this video. There's going to be some overlap in my presentation because I overshot in my presentation and I had recorded the fourth part earlier, so I'm sorry about that. That's just no oversight on my part. I should have organized that a little bit better.